Okay, the audio system seems very strong here. I can't tell whether I should speak softly or more loud. Can you everybody hear me? Okay. So uh, the I'd like to just quickly acknowledge the graduate students who worked with me on this and move on to the main point. So in physics, we all learn equations. And these are familiar equations like Schrodinger's equation, F equals ma, the circuit laws, and the Maxwell equations. So we're accustomed to equations. But there's another way of approaching physics that's completely equivalent. That is that physics can be expressed as inequalities. And some of these are famous inequalities. The For example, here's one I'll mention quite a bit today, is the second law of thermodynamics, which is famously an inequality, is that you are constantly increasing the entropy of the universe. And there are other inequalities here, maybe the variational principle, principle of least action, and so forth. Now, I've actually ordered this list, which are the inequalities that are most used for optimization, because every inequality is pushing a physical system in one direction. And therefore, it does optimization. And these inequalities are a different way of looking at physics and at optimization, is that the physics itself has optimization built into it. And we have a number of inequalities in physics that we can use. I have 6 of them listed, and actually only 2 of them are in common use. And I'll mention those as we go along. So this is the most important slide in the talk, because it tells you that we're going to look for inequalities in physics, and these inequalities will do the work for us, free, basically. And just to indicate how important optimization is, when we're doing deep learning, we have to optimize all the matrix elements in a big matrix. So when we act on a photo, which is reduced to a vector, gives you the correct expression. So it's a major league optimization problem with many different numbers that have to be co-optimized, which is rather difficult. But this is something that we can do. And so the question is, can we use physics to do it? So one of the principles that is most commonly used, but very little discussed, is the Onsager principle. So the Onsager principle, it's a principle of physics put forward by Onsager in 1931. He did eventually win the Nobel Prize in 1968, but it's taken a long time for people to appreciate the importance of what he did. I'll give you an example of what the strange thing is. Suppose you had a circuit with 2 equal branches like this. The branches are completely equal, but you'd be very surprised if 2/3 of the current went on one branch and only 1/3 went on the other branch. That doesn't happen. And what Onsager said as well, if 2/3 of the current goes in one branch, you're going to dissipate extra heat in this resistor, and it won't compensate for the reduction in heat in this resistor, and so you'll actually you'll end up wanting to reduce the power dissipation. So that's the simplest way of expressing Onsager's idea, is that systems that are being continuously driven will adjust themselves to dissipate the least amount of heat in the resistors. Now, there's a fancier way of expressing it. So the heat is essentially entropy, so you want to produce the least amount of entropy. But he made it very general, different sources of energy, not just voltage, but temperature gradients, density gradients, and so forth. And a lot of that was what he won the Nobel Prize for. This principle, though, it's a bit controversial. Let me give you another thing that is commonly used, and that is the adiabatic method. It's part of physics, and it says, let's say you have a very difficult system with many parameters, many couplings, and so forth, and you don't know how to solve it. You want to find the ground state. So you turn off all the interactions, and it's very easy to solve when you turn off the interactions, and you get the ground state. And then you gradually turn the interactions on, which could be inductances, or it could be some other component you gradually vary. And then you have an avoided crossing so that you end up solving for the ground state of a system with very hard interactions that are very difficult to solve. So this is seemingly a classical method. It's another picture of the same thing. The But it's also been elevated. It can be used in quantum mechanics, in which case it's called quantum annealing. And in fact, what I'm showing you are the origins of most of the papers in this field of physics-based optimization or physics-based computing, and that is that they tend to use either of these two methods. I would say 70 to 80% of the papers are using the Onsager principle, often without knowing it, and maybe 20, 30% are using the adiabatic method, but that's largely a company called D-Wave that originally claimed to have a quantum computer, but it's now recognized that it's using the adiabatic principle. It's not bad, but it's not exactly a quantum computer. So this is the one thing that I don't see used, and I was very puzzled by it when I made up my list, is why isn't anyone using physical annealing or even simulated annealing to do an optimization problem? So what you have is you have a system starts out here, it falls into a minimum, then somehow gets out of the minimum. It's a local minimum, goes into another local minimum, and then finally finds a global minimum. Okay, and this is basically the second law of thermodynamics: is that everything tries to go to the lowest energy level. It gives up its energy and just falls into this lowest level. Nobody uses this, and so I was very puzzled by that. So that's what I'm going to talk about in this talk is, can we use this most familiar of physics inequalities, that systems want to go to the lowest energy level? Can we use that for optimization? And so I have my list here, and the Onsager principle is used a lot. Adiabatic method is used, let's say, by D-Wave. Second law of thermodynamics is not used. And why? Okay. And then there's these other methods that are not used either. And maybe sometime at some point in the future, someone will figure out how to use those effectively. Okay. So what's used? Okay. So this is the adiabatic method. And this is the Onsager principle. So this slide is meant to explain the Onsager principle. It has the word entropy in it, but don't confuse it with thermodynamics. So in thermodynamics, you're near equilibrium. And in the Onsager principle, you have continuous power input. So the system can never reach equilibrium. Okay. You end up, if you follow Onsager, is you have the minimum entry generation, which is say the least amount of heat in the resistors. And in thermodynamics, you can do annealing or simulated annealing, and you end up with the second law of thermodynamics, which is okay. And what that law says is that entropy is always going to a maximum. So it's fine. We ought to be able to use it. Why aren't we using that? On the other hand, the Onsager principle says minimize the power dissipation in the resistors. Now you see what is the difference between the two principles. This is thermodynamics. Entropy goes to a maximum. And in Onsager's picture, time derivative of entropy goes to a minimum. And the reason why the Onsager picture is very important is that most of the machines, even the machines that are being presented at this conference, I believe are using the Onsager principle, which is perfectly respectable, but it's nice to give credit to Onsager. So what I'm going to do now is to show an example of making a machine. And so one of the things that, as I'm an engineer, and I'm just trying to be practical. The world likes to present data digitally and likes to see outputs digitally. So that's doable with analog elements. You just make the analog elements bistable. It's like a flip-flop. A flop is actually made of transistors and it's analog, but it falls into two bistable states, and you let them interact, let's say through these resistors, and hopefully you solve something interesting. So the problem that is most canonical is the icing problem, which I can express in the following way, in a very domestic way, is that you have some refrigerator magnets and you put the magnets on the kitchen table and you want to arrange the magnets in such a way that they have the least amount of magnetic energy. And it's tricky because sometimes north poles get close together and they repel each other, you get excess energy, etc. So it makes it a very challenging problem. And in fact, the problem is NP hard. That is to say, the most difficult class problems in computer science, whose solution can only be guaranteed by checking every possible solution one at a time until you find the right one. So it became rather famous in computer science. And the fame largely came from one of my colleagues, Professor Richard Karp. I think, in my view, he is the most famous professor at Berkeley. And he 50 years ago, he said, if you can solve the icing problem, then you can solve 21 different problems in computer science. And I don't recognize them all, but I recognize max cut and job sequencing. Job sequencing used to be called the traveling salesman problem, but now we call it the Amazon Prime problem. Okay, and then there's things with packing, and this is like trying to load luggage into a car when the family goes on vacation. So now, of course, that's 50 years ago. Now there are maybe 10,000 very hard problems in computer science that you could solve if you could solve the icing problem with the magnets. So what happened in the past 10 years is a great many physical machines were put forward to solve the icing problem. And one of the first people to really make a strong effort, this Professor Yamamoto from Stanford, he had an optical implementation with something called an optical parametric oscillator, which is basically a bistable element. So he built it out of bistable elements, and he was very surprised it solves icing problems. There are other schemes, for example, electrical schemes. I have a colleague at Berkeley, Jagit Chowdhury, who makes electrical parametric oscillators, but he calls it injection locking, but it amounts to the same thing. I am also kind of fond of the electrical oscillators. I'll show you a little bit of my work on this. At Cambridge University in England, very hard, still electromagnetic polaritons, which are sort of a complicated thing in condensed matter physics. But it turned out they didn't really need the low temperatures, and many of these implementations work at room temperature. Here's one from MIT that is an optimizer based on silicon photonics with feedback and gain. Okay, so all of these, so I actually wrote a paper analyzing all of these. It's very difficult to do, different physics, different notation, and so on, but we show that they were all essentially using the Onsarger principle, which I think some of them have accepted by now. So I'll give you an example of what we did. You have these bistable elements. They're basically parametric oscillators where a capacitor oscillates at 2 omega, then you have gain at omega. But the gain is phase sensitive, so it locks into 0 phase shift or 180-degree phase shift. So it's bistable in that way. And then if you connect it to another one of these things that's sort of equivalent to a magnet, but it's actually, there's nothing magnetic in it, it's just electrical. If you connect it with parallel wires, the two oscillators will lock in phase. And if you connect it with sort of anti-parallel wires, they'll lock in out of phase. And in this way, you can build up an entire circuit which has no magnets in it, but has exactly same physics. And so this is an example of something that we did. We modeled each of these oscillators running at 1 gigahertz with a bandwidth of 100 megahertz and let them run. And what happens is that it locks in after a few hundred nanoseconds, it locks in. And at 100 megahertz, the bandwidth of 100 megahertz would then correspond to maybe a clock cycle of 10 nanoseconds. And if you're within a few hundred nanoseconds, let's say 20 clock cycles, you have locked in to a definite answer. Now, I apologize for this complicated looking graph, but that's what happens. The red wires are connecting as antiferromagnetic, and the blue wires are connecting as ferromagnetics. And so in this case, it was a very extreme case. It was fully connected. And It We let it run, and after 20 clock cycles, it gave us the correct answer. So I'm not saying this is unique now. There are many groups have done this in different ways, but always using the Onsager principle. So here's an example where you might have an exhaustive search. You'd have to search through um, uh, even hundreds or even a billion different possibilities, and the circuit closes in on the one case that has the lowest energy. So that's sort of an example of what we're doing. And so it makes me very fond of the Onsager principle, that we could do things like that. And now there's something very similar. I just want to add it for completeness because I don't think they're represented at this meeting. There's a whole line of research started by Professor Suprio Dada from Purdue, where he used a different bistable element. The transistor itself can be a bistable element. And why? Because sometimes if it has very high gain, it locks all the way to a positive voltage, or the output locks to a negative voltage. And so they do that, and they have the transistors connected together. They call them probabilistic bits, but the key point is it's just another physical system that uses the Onsager principle. It adjusts itself to dissipate the least amount of heat while looking for the solution. So I think I've given you some pretty good examples of how the Onsager principle is used. This one you can look up. D-Wave has a lot of publicity, but then I asked myself, why is nobody using second law of thermodynamics? And that's what I'd like to try to resolve. So, um, what do I mean nobody's using it? Well, I don't see any papers on it, and I see there's potentially a flaw because let's say you have a circuit and you want to go to the lowest energy of the circuit. Lowest energy is there's no current and there's no voltage and there's no answer. It's rather useless. So, but we've seen some new developments, and here's a print from one of the organizers of this conference, Doug Durian, where he used a mechanical system, and it gave him a very interesting solution for uh, deep learning for a deep learning problem, and uh, it's mechanical. You see, he's got masses and springs and so forth, and clamping them and so on and so forth. So I think this is the first I've seen of the use of a mechanical system that is following the laws of the second law of thermodynamics for optimization. So I asked myself, oh, that's good, but it would be more practical if it was electrical. So looking, can I find an electrical way of having a bistable system that settles down to an interesting solution to an optimization problem? So I wanted something that was a little bit nonlinear so that I could, for example, make it bistable, maybe even address the icing problem. So the varactor is a component that is well known in electrical engineering. It's basically a diode. And as you put a big voltage on the diode, you end up with depleting all the carriers in a wider region, and then the capacitance goes down. And this thing, I just downloaded this from the internet yesterday. It goes down to 5 picofarads, whereas if you don't have such a strong negative bias, it's a little bit, the two electrodes are closer together, and it's a bigger capacitor. So it's a nonlinear capacitor. In fact, the nonlinear capacitance goes as 1 over the square root of voltage. So now, how will this help us? Because I was worried that it would just drop to the lowest energy level. There'd be no current, no voltage, and everything would go away. And it's not quite true. For example, in electronics, you have a time scale, the RC time, and let's say you let a system run and it gives you some interesting answer. And but the RC time is typically nanoseconds. It's good. It gives you a very quick answer. But there's another time in electronics that is often overlooked, not discussed very often. It's the dielectric relaxation time. So if you take an insulator, after a certain time it leaks and it's no longer an insulator. That's called the dielectric relaxation time. So Obviously, if you wait for the dielectric relaxation time, it's going to be a useless system because everything's going to go to zero. So you have to do you have to separate these two time scales, which is relatively easy to do. The RC times can be nanoseconds, whereas the dielectric relaxation time could be minutes to hours. And of course, you can complete all your measurements, get your answer before having to fight with that. And so the varactor has this unstable point. This is for this circuit where it's simply two varactors series, and you think the voltage would divide equally between them. Actually, it's an unstable point, and it ends up you either roll down here or you roll the other way, and becomes a nice bistable system that could be used for giving digital answers. So we put this together as sort of an analogy to the way the Onsager approach was doing, but now we're using the second law of thermodynamics, and that is that you could have two of these Wheatstone bridges made up of reactors, and it's static electricity, so there's no continuous power input. It is exactly the situation where the second law should be valid. And if you have parallel wires, they couple so that they lock into the same orientation, or you could have crossing wires, which they lock into an anti-ferromagnetic configuration. So it's this kind of a circuit that we're looking at. What it just sort of says, yeah, there are these weird components like reactors that can have some very interesting properties. They have a kind of a gain, they're nonlinear and so forth. So they're quite interesting. And of course, we can put them together just like what I showed for the case of the geometry oscillator. But in this case, I don't have to continuously put in power. But I could connect them up similar to the picture I showed you earlier, where each of these would lock into a different phase, but it would be completely electrostatic, and there'd be no power input, and the computation would just end. You get the answer. So I should go back. What's wrong? If the Onsager principle is so wonderful, why am I trying to get away from it? The Onsager principle requires continuous power input. Well, almost every circuit in the world has a power supply. Okay, and then it follows the Onsager principle, not second law. But that's rather inconvenient because you have to continuously supply power, and you have to know when to stop supplying power, and so it looks like it's way more efficient to use the second law of thermodynamics. It just settles down, and you get your answer. So let me arrive at some conclusions. So I would say that we have underutilized the second law of thermodynamics, and it may turn out to be the most convenient inequality for physics-based optimization, but we have to be a little bit clever about separating the timescale of the computation from if we do it electrically, there's inherent leakage and so forth. It's different from mechanical systems. In principle, there's leakage in mechanical but they're very stable over the long run. Maybe the electrical systems can't sit around quite as long, but they have many other advantages. And if we compose this of reverse bias p-n junctions, which is essentially what is a reactor, everything in chip design is about reverse bias p-n junctions. So the chip designers are definitely going to love this. Okay. And on the other hand, let's not overlook the Onsager principle because it applies to living organisms. So living organisms we all live because we have a concentration of energy-rich molecules, ATP. And this concentration is above the normal thermodynamic concentration. It's an excess concentration. So it has free energy, and that free energy is called a chemical potential. And so from the beginning to end of life of a living organism, the organism is out of equilibrium with the world. It has an internal battery, if you like, the ATP, and so it's like a power supply. And so, in that sense, the Onsager principle would seem to be more applicable to living things. Although I've gotten into very severe controversies with biology experts, and they can't reduce biology to some physics law and so on. So they hate that, but it's something I think it's worth bringing up, and I'm very grateful that there are so many biologists here this week. I hope to talk to some of you. Thank you.
Thank you very much, Eli. Any questions? So start with Edwin.
Yeah, so thanks for the interesting talk. For a machine using the second law, for example, trying to solve a spin glass problem, do you think its time to solution could just be directly related to like the relaxation time for metastable states?
Uh, I think that's a complicated technical question because you could regard a spin glass as the machine itself. But then you said, well, is it a good machine? Is it going to take forever to relax into the desired configuration? So I think what seems to be emerging in this field is that, well, the spin glass is very difficult to deal with as a physical system. It takes a very long time. Let's model the spin glass with a different physical system that has the same physics, but it gives you the answers very, very quickly. And
my thinking was like one sort of distinction between that and on-target principle machines would be that because you're constantly driving the system, time to solution, at least for certain problems, might not be sort of constrained by the physical relaxation time of the problem itself.
right, I think that's the idea behind most of the physics-based machines. The spin glass is a rather unfortunate example because it's extremely slow. But what we see is the emergence of physical machines that have the same physics as the spin glass, the same Hamiltonian as the spin glass, but it works much more rapidly.
Thanks for the talk. So I think a lot of these Onslaught principle type computing systems, part of the reason we are doing this continuous power input is to like program and like turn on and off systems. It's nice that there is an old state and then you turn on the drive.
Yeah.
And you end up in this granted of some problem you programmed.
Yeah.
Do you have any thoughts for how you could achieve a similar thing with these second law type systems?
Okay, so that's a really good question. And that's exactly what stimulated me to organize this talk. Obviously, there's way more flexibility in circuits with batteries. They do everything for us, right? They are cell phones and even this wireless microphone that I'm talking on. So we can do everything in that situation. In the situation where it has to be electrostatic and there's no power input, we have very little experience. So part of what I tried to do in this talk is to come up with a credible device that would potentially solve interesting problems. That was purely electrostatic, that would just fall to the lowest energy level and do something useful for us. So I think it's in its infancy. I don't guarantee that this is the best way to do it. I would say it started with Durian doing it with a mechanical system, and now an electric system. And I think there's potential there, but we can't be 100% certain that we could keep up with the normal electronics, which has power supplies.
I didn't quite get whether your varactor network spontaneously goes to the ground state, or you have to kick it out of local minima the way you drew the.
Okay. So that's a very good question. Almost with every type of machine that when we search for a global optimum, eventually we're disappointed that we get stuck in the local minimum. And what I see developing, I didn't have time to put this into the slides. It's not my work, but it's the work by Durian, where he builds in memory, and by building in memory, you can more closely approach deep learning. Also, a rather related work from Professor DeVentra from UCSD, and he calls it mem computing. So he builds memory into the individual gates. The essential point, according to DeVentra, is that in effect, in every gate, there are extra degrees of freedom. So if you get stuck in a local minimum, what's going to happen? The extra degrees of freedom will convert the local minimum into a saddle point. You'll fall out of the local minimum, and you'll continue on the way toward the global solution. But that's sort of a strategy that they have. I don't think they've I don't think there will ever be a proof that you can always find the global optimum.
Can you illustrate a bit more like how, some of the principle, how to link the minimum dissipation to the minimum energy in some like icing machine problem?
They're both competing approaches. They both represent two different physical laws. So I showed you a slide where on the right side was the second law of thermodynamics, on the left side is Onsager. Okay, and they're both inequalities that look like they could be useful for optimization. The second law gives you maximization of entropy. Onsager gives you minimization of time derivative of entropy. So it's two different things, and they're both useful. They have their advantages and disadvantages, but they're not. One is not the same as the other. They're just different competing approaches. Follow up.
For the second law of something, it feels like lowest energy. Are you referring to like the Ampere's free energy in this case?
Yes, the second law gives you the lowest free energies. It's seeking out the lowest free energy. Free energy is U minus Ts, so it's maximizing the entropy.
In your linear capacitor setup, do you have a conservation law for the field amplitude or the Hamiltonian in that system?
Well, of course, we do have a Hamiltonian for it, and that gets minimized, and it's similar to the Ising Hamiltonian. But the question maybe you should be asking is, the first law says energy is conserved. Where'd the energy go? And so, but this is the same question every time you have the chemistry teacher says your molecule goes to the lowest energy level. Where do the energy end up? It ends up as heat. And so that's part of the second law is that you're always casting off energy and so that you can fall into the lowest energy state. And so that's the inequality of the second law of thermodynamics.
Is there a way to compare apples to apples, the two approaches where I'm assuming in the second approach, the energy consumption is in the kicks to get it out of the local system? And so is it provably to say that the two solving the same problem, one of them will end up using less?
Yeah, I think you're describing just one of the energy contributions. I think of them as rather two different schemes, but the normal circuits are way more flexible and adaptable, and we live with them every day, and they're very useful to us. The one with the varactors is essentially electrostatics, and in principle could be more efficient, but it's still in its infancy. If you asked me a few months ago, I said, no, we can't do anything with the second law because all the currents and voltages go to zero and there's nothing to study. So this is very much still in its infancy. I wouldn't say they're competing because you can do so much more with conventional circuits. But we see the beginnings of using the second law for optimization.
Good question about just what it means to solve the goal of solving the Ising model. So is that challenge, does that challenge require all nodes to be connected to all of their nodes, or does it count if I solve it when like everybody's connected to 6 other nodes?
Okay, so in that field, normally full connectivity is much too demanding. So the people in that field regard that as a hopeless case. We just did it because our systems were limited in size, and so we made them more complicated by fully connecting them. So what you end up with is your list of magnets or your list of bistable systems. You end up with a binary string. So 1, -1, -1 plus 1. The minus ones you make zeros. It becomes a binary answer to a challenging problem. But I should say that even with the best machines, it's a limit. There's still a limit in the size of the problem we can solve. How many? I think 100 spins is extremely respectable. 100 magnets is extremely respectable for a physics-based machine.
I think we should call the end of the session. Thank you.
Thank you.